Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So today we are going to finish this lecture on white column stores, which is basically HBase or big table. After that, we will move over to data modeling and especially data frames and validation. So where were we? So last time I told you about this mystery. How can it be that HBase has a low latency? You can read and write, it's almost immediate. And yet it's on top of HDFS and the data is stored on HDFS. But you know that HDFS doesn't have a low latency, right? When you access something on HDFS, it takes time. So how can it be that HBase is actually low latency? And then I told you the secret. The secret is that the data is in fact the recent data, the fresh data is kept in memory in the mem store, and then it is flushed in a single go as a sorted sequence of key value pairs to HDFS, but that doesn't happen all the time. It's only when the memory is full. And then we saw that when you start having many files that were written, then you start compacting them to larger and larger and larger files over time. So there's flushing and compaction. Right. In fact, somebody asked last time about caches and how it relates to the caches that you might have, like L1, L2 caches with the CPU. It's kind of related, although on a higher level. In a way, you could consider that the mem2, the mem store, is a write cache in the sense that it's data you put in the cache that is not yet propagated to or that hasn't been written back, right? So you could, with the comparison, consider that the mem store is a sort of cache in the direction of writing. Now, as it turns out, we also have a cache in the other direction, which is when you read. So it's just not the same thing as the mem store. So you do have in memory a copy of some of the data that is actually on HDFS because it's old, but you still maintain a copy of some of them in memory. Why? Because maybe it was used recently, or maybe because you use it often, right? So it's a typical criteria for inclusion in a cache. So that means that the key value pairs that you access a lot or that you've accessed recently are also in memory. Then you don't need to read them from HDFS, right? This is the point at which I should mention that when you cache, this is done at the level of these H blocks, right? You don't do it with individual key values, but you load it H block by H block, right? When you put it in the cache as a copy. So I hope it answers the question of last time, how it relates to caches. So again, you can see this cache that is with very old data. You can see it as the read side of the cache, but you never write back to it. And then the mem store as the right side of the cache where you have the data that hasn't been persisted yet. For whom is this clear? Right? Okay, very good. Then there are cases where the cache is totally useless, at least the reading cache. First, it's when you batch process. We will see with MapReduce and Spark that there are cases where you need to read all of the data, all of that. You have a data set that is 1 petabyte, and you need to read all of it. Here, the caching is totally useless because you anyway need to read all of the data, and you only read it once. So the cache then is totally useless. We'll see how it's called, why it's called batch processing very soon. And the other reason it might be totally useless is when you have random access. You just access the data totally randomly and there's no pattern, there is no hotspot. So a hotspot is what you call the regions that have a lot of reads or a lot of writes. So if there's no hotspot and you really just access the data randomly, the cache is totally useless as well, right? So you always need to think, depending on your use case, depending on your access patterns, and that depends on the project, if it's actually helping to have a cache. Nevertheless, the mem store is always there, and this you need in any case to when you write the data. Then there are a few optimizations because, as I told you, so flushing and compacting is obviously already an optimization because you have less files to look at. But basically, the difficulty here is that whenever somebody wants to read key values, you need to look everywhere. They could be everywhere. You need to look at the mem store. You need to look at every single H file because you never know. There could be key values that you're looking for absolutely everywhere. So you have to read everywhere. Can you do better than that? Yes, if you have extra information that you have the guarantee that an H file is not going to contain anything, then you can skip it. How can you have this guarantee? Well, you have two ways, basically. There's many others, but I'm going to explain these two. The first one is that you might have in every H file some information about the key range that is in there, like the minimum key and the maximum key that is in there. And if you're looking for a key that's not in that range, you can just keep reading the H file entirely because you know for sure that it doesn't contain anything you're looking for, right? So this is one way. It's actually not just for HBase, but very common to many big data applications that you can optimize in that way. And the other way is called the Bloom filter. A Bloom filter is what I think in Eastern Swiss German you would call the Petäterli. It's something that maybe tells you the truth, but you're not quite sure. The idea is that it's telling you that for sure the key is not going to be in that file. So in that direction, you can be certain. So the Bloom filter is going to tell you for sure nothing you're looking for is in there. Then you skip it. But in the other direction, there's no guarantee. Basically tells you maybe a key value is in there. Maybe yes, maybe no. It's not impossible, but I'm not saying no, right? So it's really a maybe answer in the other way around, right? So it's asymmetric, right? If the answer is no, you're sure it's no. If the answer is yes, that's actually a maybe. Okay, so this is a Bloom filter. You might have exercises actually on that because it's quite interesting the way it's done. It basically uses a combination of hash functions. So you have some sort of bitmap with bits. And then whenever a key is written, then you update the bitmap in such a way that because of the properties of the hash function, you have that guarantee that if it's false, then that's certainly a true negative. And if it's, and in the other way around, if it's true, then that's a maybe. Okay, so that's a Bloom filter. Everybody is with me? So the one thing here that is very important and that you have to remember is that this is not just this sort of things is not just for HBase. That's a very general thing in big data. When you have data that you have to read for a lot of files and you need to locate data in there, you want to optimize with extra information so you don't need to read all the files and you can skip some of them in order to improve performance. Okay? All right. Now, I would like to say a few words about the Bootstrap, because this is a question that some of you asked me offline, and I haven't really explained it. I might have mentioned it, but not really explained. It's how do you know where the regions are served? How do you know which region server serves what region? So the first intuition, if you think of HDFS, might be, okay, maybe the HMaster knows that, and you need to ask the HMaster every time. Just like you connect to the name node when you want to know where the blocks are in HDFS, right? So a first ID might have been the HMaster. But in fact, that's not the case. The HMaster is really not responsible for knowing or keeping track of where the regions are served. It's only responsible for creating tables, deleting tables, you know, these sort of tasks. But the part about keeping track of the regions is actually delegated or outsourced somewhere else. That somewhere else, in fact, is one of the region servers that holds what's called the meta table. That meta table is actually a table like all the others, but not exactly like all the others, because the first difference between the meta table and the other tables is that it's small. It's actually maybe a few megabytes. So it means the meta table fits on a single machine. It's not sharded or separated like the other tables would be. It really fits on a single machine. So that's the first thing. And the second thing is that everybody knows where it is, the meta table. So when you decide, basically you can create, delete, and update tables through the HMaster. But when you want to query for a region and know who is responsible for a region, you just connect to whichever machine holds the meta table. How do you know where that meta table is. How comes everybody knows it? This is with the magic of distributed system protocols that are outside of the scope of this lecture, but it's basically the idea of having a peer-to-peer network of machines that is able to elect a leader and that is able to synchronize and agree on some truth, right? And so this piece of software, I mentioned it last Wednesday, is called Zookeeper. Zookeeper is a distributed systems technology that allows all the machines to kind of know where that meta table is, right? So this is done with some quorum protocol that is a bit similar to what we saw in key value stores. But I don't want to talk to you about it because, again, that's outside of the scope of this lecture. So that you can see in Professor Wattenhofer's lectures, for example, on distributed systems and Paxos and blockchains, which is very interesting. So for the purpose of that lecture, we take it as a given. It's magic that everybody knows where that meta table is on that server right there. So whenever anybody wants to query data, they just ask the region server that has the meta table. And based on the answer from the meta table, then you know where you request the regions. And that you do directly connecting to the region servers. There's no need to go through the HMaster for that, right? So it's really decentralized, okay? If you look at the meta table, in fact, what there is in there is just a list of all the regions, all the tables and all their regions. And for every region, you have the interval of the keys, so the minimum included and the maximum excluded. You have the IP address of the region server that currently serves that region. You have a flag that tells you if that region is actually in the middle of a split, in which case you must be careful, and so on and so on. Right, so this is what there is in that special table. And that is what gives us the bootstrap of everything. And this is why everybody knows what is stored where, okay? Now, I could also say a few words about the split because people ask. I don't have slides, but I can explain a little bit. You remember that if a region grows and grows and grows to the extent that it's actually becoming very difficult to manage for the region server, then the region server is going to split that region into two regions. So if you consider that the split happens immediately, it means what do you need to do basically? You need to make sure that the meta table is updated because it needs to know about the split. So instead of one row, you're going to have two rows with each half. And you need to make sure that the H files after the split will be split too, right? If the H files contain the whole region and you split the region, then it means that every one of these H files also need to be split into, right? Who agrees? Who sees that? Right? Okay. But the thing is, in order to be efficient, that doesn't happen immediately. In fact, when you decide on a split, what actually happens is that it's cheating. It's basically pretending that it's already split. So what happens is that in the meta table, you add this flag saying careful that region is split, and these are the new regions, and this is which machines are serving them. And then the clients that connect will see that it's undergoing splitting, and they are going to connect individually to the two halves, depending on what they are looking for. And when you connect to the region server handling one half of it, the region server at first will have to read the old H files, the H files that contain the whole region. It just needs to ignore the other half, right? So it's a temporary measure that you're still using the old data, you're still using the old H files, but you're just ignoring the other half. And what happens is that with time, but this is asynchronous, at some point, whenever you need to do flushing or compaction, then you will split it. You will start splitting the H files as well over time, either actively or as a reaction to compaction. For whom does that make sense? Right? So it means the split is efficient, right? You start with pretending that it has been split, but you still work with the old H files. And over time, you start also splitting the H files and the mem store. Okay, so that's the high level on how it works. Again, so if I summarize, you still connect to the HMaster to create, to delete, to update, meaning you add a new column family, you remove a column family. But if you just want to read data, you directly connect to the meta table, and you know where it is thanks to Zookeeper. And then you connect based on what the meta table told you, you connect directly to the region servers that serve your region. Okay, so now you should have this high-level picture of how HBase is actually working. Okay, HBase has multiple APIs. That's nothing really new. There is a REST API. You can also access it via Java. You also have a shell commands to access it, and we'll see that you can also access it via MapReduce and Spark also later. So now we are approaching the end of HBase. I wanted to say a few words about data locality. And in fact, I'm going to end up repeating some things because since you asked questions, I already mentioned it a little bit. So the idea is that HBase and HDFS are running on the same machines, right? So it means the HMaster is on the same machine as the name node, and the region servers are on the same machines as the data nodes. And because you might remember that when you flush or compact something on a region server, the first replica of all the blocks will go to the same machine because the region server is a client of HDFS. And we saw that when you're a client of HDFS, the first replicas of all the blocks you write go to the same machine. So it means that this region server sitting on that machine is going to write the first replica of all its blocks on the same machine right here. So it means that you can short circuit the whole thing whenever you need to read the data. You don't even need to go to HDFS to the name node, or you can cheat basically. So the region server might be aware that there's a copy of all the blocks, and it will just read them locally on the hard drive. It's the same machine, it's the same operating system, it just reads the file locally, the blocks of HDFS locally. So it's very, very efficient because you have a copy of the blocks on the same machine. But over time, if you activate the load balancing mechanism of HDFS, the blocks might get spread all over the cluster. There was a question, by the way, that you want to look at on the forum, that this load balancing can be either manual or you can set it up as a service that runs constantly. But basically what happens with the load balancing is that if at some point there are less blocks at some places and more blocks at other places, the blocks might start going somewhere else. Right, so then you have to read them remotely and you can no longer short circuit, right? For example, if you're the region server and you need to read that block, you need to go over the network because that's another machine. So it's less efficient. So you could deactivate, of course, the load balancer if you want, the risk of having some imbalance. But anyway, even if you have the load balancing, what happens is that the next time you do a compaction, it will bring all the blocks back to the machine. Because when you compact, you're writing a new file. And when you write that new file, all of the first replicas of each blocks will go again to the same machine, right? So every time you compact, every time you flush, you bring back a copy of every block to the same machine, okay? Who understands this, right? Who understands the concept of short circuiting, right? It's the benefit of being two Hadoop teams. HDFS is Hadoop, HBase is Hadoop, so they can a bit cheat by basically directly going to the hard drive. Okay? So it's a breach of data independence technically to do it because you're breaking the rules of HDFS doing that, but that's kind of okay because it makes it faster and again, it's the same Hadoop projects. All right. So HBase is meant to be used on one cluster, a cluster where there's already HDFS. Typically, the machines are going to be in the same data center, but there's been some work done since then. There's newer versions of HDFS that span multiple data centers. It was called, now there's probably something new that we don't know about, but it was called Colossus, the successor of GFS. And the successor of Bigtable is called Spanner. And now I can just show you, because this is really optional and as a bonus, but just to basically show you the direction that this is taking. The idea of Spanner is it improves over HBase first because you can have multiple columns for the primary key. You remember that in HBase, it's just one column. It's the row ID, and the row ID is the primary key. Well, in Spanner, you can have multi-column primary keys, right? You don't not just one, but multiple of them. The other improvement is that instead of restricting the regions to single intervals, in Spanner, you allow for multiple intervals in the same region. That's called the tablet. So you might have an interval here plus an interval here, and the two together give you a tablet. So there's a relaxation of the constraints that the regions must be in a single as a single min-max interval. Okay. Now, what actually is quite impressive is that you need to actually pause and count the zeros here, right? So if you look at it long enough, you will realize that you're looking at 1 trillion in here, right? 12 zeros, trillions of rows. This is absolutely gigantic, and that grows very, very big. And in fact, because it grows so big, you cannot just use one data center or one cluster. You need multiple clusters. So it basically means that everything we knew about HBase that corresponds to this, basically, where you had the HMaster and the region servers, but now you have multiple of these, maybe at different locations around the world. And now you have what's called a universe master in here. That is basically the emperor of the universe and basically handles all of these locations. So this is how you achieve scalability to trillions or quadrillions of rows and absolutely enormous scales. Now you can imagine as a university, you don't get that. You need to be a company large enough to be able to afford these things. But this is basically what is done by some of them. And then you're really considering, like what I showed here is just 5 of them, but actually you have to consider hundreds of them, hundreds of data centers all over the planet that contain that, right? So this is Spanner. And again, I'm just showing you the high level overview of that. We are looking at millions of machines here that store it, right? Okay, so of course you should not be afraid of very, very large numbers because this is really impressive what we managed to do today. Okay, so this is my last slide actually about Spanner. Again, that is bonus, right? What I'm telling you, all of that, this is just for the fun, that I'm telling you that you even have this way of going across a single cluster. Okay, do you have any questions, anything on HBase? Yes, maybe we can give the microphone.
Why would anyone need a table that is this big and not just store something in like object storage?
So I think that, so we don't know everything first, because these are companies that might have proprietary information, and so they do not tell us everything. I could imagine multiple reasons for that. So the difference between object storage and white column storage is basically the dimensionality of your indexing. So basically, if you're looking at object storage or key value storage, the keys are organized as a single dimension, like a ring in the case of a key value store. But even for object storage, you just have a bucket ID plus object ID. It's a single dimension, right? The difference between this and white column storage is that in white column storage, you still store objects. Basically, if you look at these, all of these are objects. All of the cells here are objects. They can be big. They can be dozens of, up to 10 megabytes. But the idea is that now these objects are organized in a grid. It's no longer just a one-dimensional thing. They're in a grid because they're indexed both by these keys right there. That is 1/2 of the way to identify them, plus the columns, right? And you have a lot of sparsity because a lot of them are actually going to be empty. So this is the main difference. So what you get is a system that will not store very large values of gigabytes level, for example. For that, you should use the object storage. But if you want to store smaller values like HTML, XML, JSON documents, and so on as blobs, then you could store them in there as a two-dimensional grid. Right? Does it make sense? Okay. Another question over there.
What is the advantage of having a region that is not like one connected sequence?
Connected components. That I'm not really sure. My intuition would be that it might give you a bit more flexibility for several reasons. I'm thinking in theory. The first reason is that we saw that you can split regions, right? But imagine that at some point it's the opposite. Regions become too small and you want to merge them together. Do you see that if you have tablets like this that don't require contiguous intervals, it's easier to merge tablets than it would be to merge regions, because the regions you could only merge if they touch each other, if there's exactly the max exclusive is the same as the min exclusive, right? So basically having tablets gives you more flexibility for splitting and merging because of the mathematical closure under this. Does it make sense? Right, but that's only a guess because again, I'm not exactly sure of the maybe it's actually there's probably a paper that we could we could look into. Mm-hmm. Yes.
Thank you. My question is like, what is the reason for storing this meta table on a region server? And doesn't it again introduce one single point of failure for the whole system?
So I start with the single point of failure. The reason why it's not a single point of failure is that so first the data is stored on HDFS, so you will not lose it if there is any problem. And then what happens is that if that machine crashes, all you need to do in Zookeeper is just switch to another one. That's basically called electing a leader in distributed systems. So we just have the people response, not the people, the machines. Maybe soon we won't see the difference, but anyway. So the machines responsible for the meta table will decide on a new location for the meta table, and that's very quick. That's the Zookeeper protocol that basically takes care of that. Right.
Why isn't it stored on the HMaster? What's the reason to load on the HMaster?
I think the reason is that when you serve the meta table, you have to have all the code, the computer code and the process that knows how to serve tables, basically. And the HMaster doesn't have that. In the HMaster process, there is no code that would allow you to serve a table. So this is why it's more natural that this table is seated on a region server, because the region server will serve the meta table with exactly the same code as any other region. So that's probably one of the reasons. Yeah. And there might be, I mean, I don't know how HDFS is going to evolve, but basically, for example, we use Zookeeper to elect the HMaster in HBase. In HDFS, as far as I know, they don't do it yet. So in HDFS, they don't use the Zookeeper. Sorry, I mean for the heartbeats. For the heartbeats, the region server sends the heartbeats via Zookeeper, and then the HMaster knows which one are alive through Zookeeper. In HDFS, that's not the case yet. In HDFS, the data nodes still send their heartbeats directly to the name nodes. But I suspect that at some point, it would be a natural step that HDFS could take, that they also move over to Zookeeper for doing this, because that's the intent of Zookeeper, right? So this is also why it's important, you know, I'm showing you actual systems that were designed. But what I really want you to do is to think of it with a bit of distance, having in mind that this will change, it will evolve, and you really need to focus on the high-level considerations, the high-level considerations of the choices that were made. And the choices are not forever. It might be that people have a brilliant idea in 1 or 2 years, and they figure out something with a change of design that actually turns out to work better, right?
Thank you.
Thank you. No more questions? On Zoom? No questions? Doesn't seem so. Okay. So don't hesitate. Of course, if you have questions after the lecture, you can ask them on the Moodle forum, and we will do our best to answer them. So I'm going to stop the recording here.